Welcome to the Deep Dive. This is where we take a whole stack of information, articles, research, and we really try to pull out the most important bits of knowledge, those key insights just for you. Today, we're diving headfirst into a concept in Java programming that's, well, it's always been important, but maybe now more critical than ever in this complex world we're in. We're talking about immutability.
Right?
We've got insights here from a pretty comprehensive source. Immutability in Java.
Yeah.
Concepts, string implementation, usage, and importance. Our goal, give you that shortcut to being really well-informed, maybe point out some surprising things, and hopefully keep it interesting.
And what's fascinating, I think, is how immutability sounds maybe a bit abstract, right? But it quietly props up the stability, the security, even the performance of so much software we use every single day.
Really?
Yeah, it's all about designing objects so that once you create them, that's it. They cannot be changed. And this deep dive, hopefully, will show you not just what that means, but why it's actually incredibly powerful.
Okay, let's unpack that then. When we talk about immutability in Java, what are we really defining? What does it actually mean for an object to be, unchangeable after it's made?
So immutability in Java it just means that an object's internal state, think its data, its fields, that stuff can't be altered after it's been initialized.
Okay.
Think of it like carving something into stone. Once it's done, it's fixed permanently.
Right, like set in stone.
Exactly. So key traits you'll see. All the fields are usually locked down, maybe using final, preventing reassignment. There are absolutely no methods like setters that could modify the state.
No setters all.
None that change the internal fields. And importantly, if the object holds references to other things that can change, maybe like a list,
Oh, okay.
it has to be careful. It provides copies of those things, never the originals, to block any external changes. It defends its own state.
Defensive copies, got it.
Right. And this also means, critically, that any operation that looks like it's modifying an immutable object, it isn't. It's actually creating a new instance with the changes.
The original is always preserved, untouched.
So wait, if I have one of these objects and I want to, let's say, update it, I'm not actually updating it. I'm getting a completely new one back.
That's exactly right. You get a brand new one.
Wow, okay. That feels like a really fundamental design choice. So how do developers actually, bake that immutability into a class? What's the process?
This is very deliberate, yeah. To make a class immutable, developers follow a kind of recipe. First, they usually make the class itself final.
So it can't be extended?
Precisely. Prevents subclasses from messing with the immutability.
Yeah.
Then, all its fields are typically final and private. They have to be initialized when the object is created, like in the constructor.
Okay.
Any mutable components it might contain. Like we said, protect them by making defensive copies. Never let the original references escape.
Right.
And crucially, just don't provide any methods that could alter its state. Period. You've probably used immutable objects tons of times without even thinking about it.
Oh.
Java's standard library is full of them.
Oh, yeah. Well, the big one is string, but also things like the wrapper classes, integer, long, the datetime classes like local date, all immutable.
Okay, string. Here's where it gets really interesting for me, because string is everywhere in Java. It's so fundamental. And you're saying it's a prime example of immutability. How does it actually do that, like under the hood?
Oh, string is basically the poster child for immutability in Java. It's a master class. First off, the class itself is final. Can't subclass it.
Okay, checks that box.
Yep. Internally, it stores the characters, the text data, in a private fixed structure, usually an array that cannot be reassigned or accessed directly from outside.
Right, hidden away.
Exactly. And most importantly, look at the string class methods. There are no public methods that actually change the content of the string object itself. None.
But wait, what about methods like to uppercase or replace? They seem like they change the string.
Ah, that's the clever part. They seem like it, but they don't. If you have a string hello and you call it to uppercase, it doesn't touch the original hello object.
It doesn't.
No. It creates and returns a completely new string object that contains hello. The original hello is still floating around unchanged.
Huh. So if I, concatenate strings, if I take hello and add world to it.
Same deal. You're not actually modifying the original hello.
Wow.
That operation creates a brand new string object containing hello world. The original hello and world strings remain exactly as they were. Any action appending, replacing, trimming, whatever, results in a new instance.
Okay, that's That's quite something. It sounds like it could create a lot of objects.
It can, but Java has optimizations, and this design enables a really powerful memory optimization called the string pool or string interning.
String pool.
Yeah, because Java knows strings are immutable, it knows they can never change. So if you have the same string, literal, like hello, appearing multiple times in your code,
Ah,
Java can store just one hello object in a special memory area, the pool, and have all the different variables point to that same object.
so it reuses them.
Exactly. Saves a ton of memory, especially if you have lots of repeated text. This is only safe because strings are immutable. If they could change, sharing them like that would be chaos.
That makes sense. One change would affect everyone pointing to it.
Precisely. And it helps with security, too. If you create a string from something mutable, like a character array, string doesn't just hold on to your array, it makes its own private copy internally.
Another defensive copy.
Yep. So even if you change the original array later, the string object remains unaffected. Its immutability is protected.
Okay, so beyond just being this kind of elegant design pattern and enabling things like the string pool, why do developers actively choose this? What are the big practical wins? Are there any downsides, like performance maybe?
That's a fair question on performance because creating new objects isn't free, but often the advantages are so significant they outweigh the costs, especially with modern Java virtual machines being so good at garbage collection. The first massive advantage is thread safety.
Concurrency.
Yes, immutable objects are inherently thread safe. Because their state cannot change, ever, multiple threads can access the same immutable object simultaneously without any need for locks or complex synchronization.
So no synchronized blocks needed for just reading them.
Exactly. You just eliminated a whole category of nasty bugs like race conditions and deadlocks that plague concurrent programming with mutable state. It drastically simplifies building concurrent apps like web servers or back-end systems.
Wow, okay, that sounds like a huge win for just preventing bugs. A whole class of them gone.
It really is. It's a bug-squashing superpower. Secondly, you get predictable behavior. Because the object state is fixed, it behaves consistently. There are no unexpected side effects from some other part of the code changing it underneath you.
Right, you know what you're dealing with.
Exactly. This makes code vastly easier to reason about, to test, to debug, and ultimately to maintain, especially in large, complex systems. That predictability is gold.
Okay, thread safety, predictability. Okay. What else?
Then there's memory efficiency. We talked about the string pool. That kind of sharing and reuse is possible, saving memory. And while new objects are created, often references are just passed around, and the garbage collector is very efficient these days.
And you mentioned security earlier, too.
Absolutely. Security is a major benefit. Immutable objects are fantastic for holding sensitive data. Think configuration settings, maybe cryptographic keys, user credentials.
Things you really don't want accidentally changed.
Precisely. Once created, they can't be tampered with. In networked applications or security contexts, this provides a strong guarantee against malicious or even accidental modification of critical data.
Makes sense.
And finally, they really simplify caching and reuse. Because an immutable object's state never changes, its hash code, if calculated, will always be the same. This makes them perfect, reliable keys in hash maps or other caching mechanisms. You don't have the weird issues you get when a mutable key changes after it's put in a map.
Yeah, that could be messy.
Very messy. And stepping back a bit, this whole philosophy aligns beautifully with paradigms like functional programming, which heavily emphasize creating new data from old rather than modifying data in place.
Okay, so lots of solid advantages. Thread safety, predictability, memory use, security, caching. But the source material really emphasized that immutability remains critical in 2025. And looking ahead, why now? What makes it so relevant today and for the future?
Yeah, that's a key point. Its importance is arguably growing because it aligns so well with how modern software is built and deployed. Think about concurrency in modern applications.
It's everywhere now, right?
Yeah.
Multi-core processors, cloud, microservices.
Exactly. Concurrency isn't a niche thing anymore, it's the default. Immutability directly tackles the core difficulty of concurrency managing shared mutable state. By eliminating mutable state, you eliminate the need for most locks, which simplifies design, reduces bugs like race conditions, and often improves performance in these highly concurrent distributed systems.
So it's less a nice to have and more like a foundational piece for making scalable systems actually work reliably.
I think that's a fair way to put it, yes. It also directly supports reliability in large systems. In big enterprise applications, think finance, healthcare systems where correctness is non-negotiable.
Mhm.
An unintended change to some shared piece of data can have disastrous consequences. Immutability drastically reduces the surface area for such errors. It makes systems inherently more robust.
And the security angle in today's world.
Even more crucial, security in a connected world. With cyber threats constantly evolving, guaranteeing that sensitive data, once set, cannot be altered is a powerful security measure. Immutable objects become trusted components in secure contexts, whether as authentication tokens, configuration settings, or critical parameters passed between services.
And those performance benefits seem to keep popping up too.
They do. Performance optimizations like string interning are one aspect, but also the ease of caching immutable data without worrying about it changing can lead to significant performance wins in systems that rely heavily on caching, like web applications, big data processing, or real-time analytics. Less data fetching, faster responses. And as we touched on, there's the alignment with modern paradigms. Functional programming concepts, reactive programming, these are gaining a lot of traction for building resilient, scalable, event-driven systems. Immutability is a natural fit. It's often a core tenet of these approaches. Even Java itself is evolving, adding features like records, which are designed to make creating simple, immutable data carriers easier than ever.
So the language itself is leaning into it more.
Absolutely. It recognizes the value. And finally, think about legacy and future compatibility. So many existing Java systems out there rely, perhaps implicitly, on the immutability of things like string. Designing new components with immutability ensures they integrate cleanly and predictably with older code, while also being well-suited for future architectures. It helps bridge the past and the future.
Wow. Okay, what a fascinating deep dive into immutability.
Right.
We've really seen how this principle, keeping objects unchangeable once created, delivers some incredible benefits. That inherent thread safety, just wiping out whole classes of bugs, the predictability it brings, the security advantages, especially for sensitive data. And the string class, it really is a perfect example, isn't it? That fixed state, no methods to change it, and that clever string pool designed for memory efficiency.
It really is fundamental.
Yeah. It seems clear that from making complex concurrent systems manageable to safeguarding data to enabling these modern programming styles, immutability isn't just a detail. It's really a cornerstone for building software that's robust, scalable, and, importantly, maintainable over time.
Which leads to maybe a final thought for you, the listener. Given how powerful immutability is for preventing errors, for enhancing security, for bringing predictability to complex software systems, where else? Where else in your daily life, maybe your work outside of coding, could applying a principle of fixed state or unchangeable data bring a bit more clarity, maybe more reliability, or even just some peace of mind? Something to think about.